General rules of fragmentation. First, the relative height of the molecular ion peak is greatest for the straight chain compound and decreases as the degree of branching increases. So, in other terms, if there is branching, it is likely that at the branching you will get formation of fragmentation. The relative height of molecular ion peak usually decreases with increasing molecular weight in homologous series. When we talk about homologous series, we mostly think about alkanes. So the relative height will go on decreasing. Okay, the relative height of the molecular ion will go on decreasing as the molecular weight of the homologous series increases. In other words, if there are long chain alkanes, or for that matter any compound with long chains, as the number of carbon goes on increasing in the chain, the stability of the molecular ion goes on decreasing. It is more likely that it will break down quickly. So cleavage is favored at alkyl substituted carbon atoms. The most substituted, the more likely is cleavage. This we have discussed. This is a consequence of increased stability of tertiary carbon atom over secondary, which in turn is more stable than primary. So because this is more stable, it will remain as it is. Okay, so the stability, if it is a stable, it will likely to survive through mass analyzer, and like is getting detected at the detector. Something which is comparatively less stable like CH3 or RCH2, that is primary and secondary, it is more likely to get cleaved. Now, Stevensons rule: when an ion fragments, the positive charge will remain on the fragment of lowest ionization potential. Generally, we said that when there is heteroatom is present, it is likely that the heteroatom will acquire the charge. The reason being, it has the lowest ionization potential. So I will repeat the statement and you will understand it. When an ion fragments, okay, when there is generation of ion because of bombardment of electron and that ion undergoes fragmentation, the positive charge will be remain on the fragment of lowest ionization potential. Okay, generally the largest substituent at a branch is eliminated most readily as a radical. So largest group will get leaved as a radical. The reason being, if there is a long chain, it is more likely that it will be a stable radical, comparatively stable radical. Presumably because long chain radical can achieve some stability by delocalization of the lone electron. So the example is given of cleavage of 1-methyl pentane. Okay, if it has to be cleaved, first electron will be lost and there will be generation of a positively charged radical from 1-methyl pentane. Okay, how that can be cleaved? Now it has to be cleaved at this junction. Okay, it has to be cleaved at this junction. So there are two possibilities. One possibility, one of the CH3 will be removed as radical and the remaining part will acquire a positive charge. Second possibility, this 3-carbon chain will be cleaved and the remaining 3-carbon chain will acquire a positive charge. So it has to be the longer chain that is cleaved that will remain as radical and the remaining part will acquire a positive charge. So this is Stevensons rule, easy to remember. So in this fragmentation, positive charge remains on more highly substituted fragment, that is one with lower ionization potential. So if this group has got lower ionization potential, so the charge will remain on this part. Double bonds, cyclic structures, and especially aromatic or heteroaromatic ring stabilize the molecular ion and thus increase the probability of its appearance. So in your structure, if there is such structure present like double bond, or if it is a cyclic structure or aromatic structure or aromatic ring with heteroatom, it is likely to be more stable. So in the molecular ion, okay, they will be included. Okay, next rule: double bonds favor allylic cleavage and give the resonance stabilized allylic carbonium. Now When we say allylic, it is a double bond adjacent to a single bond, that is called as allylic structure. Okay, so example is, if you will see, it is 1 butene, 1 2 3 4 4 carbons, so it is butene. Okay, 1 butene to be specific. Now when it will get charged, there will be formation of charge radical molecular ion. When that molecular ion cleaves, it is most likely that the double bond will be part of the fragment carrying the charge. Okay, because when it is part of that group carrying the charge, by shifting of the double bond, that positive charge will get stabilized within the structure itself, so it will be stable. Now because of this stability, it is more likely that this kind of fragment is possible. So one CH3 will be removed from the structure to give you the base peak. Now saturated rings tend to lose alkyl side chain at alpha carbon atom. This position, this positive charge tends to stay with the ring fragment. Okay, the example is given over here. It is a saturated ring. Okay, it is not aromatic ring, it is a saturated ring. Now there is a structure in propyl cyclohexane. See, these 3 carbon ring attached to cyclohexane, so it is N propyl cyclohexane. When the molecular ion of this is produced, it is more likely that in the first step of cleavage, the 6-membered ring will acquire the positive charge, and this part will be cleaved as a radical. So you can see propyl radical is formed, and there is 6-membered ring with a positive charge. Now there is internal rearrangement. If you will look closely, it is the retro Diels rearrangement. Okay, there is shifting of sigma bonds to form a pi bond. Okay, so CH2 group will be removed. Okay, CH2 group is removed. Please note that then there will be formation of one allyl. Okay, there is formation of allylic group. Then next step, next rule, in alkyl substituted aromatic compound, cleavage is very probable at the beta bond to the ring, giving the resonance stabilized benzyl ion and more likely propylium ion in the next step. So there are 2 ways to look at this this rearrangement and stabilization of the ion. So this is N-butyl benzene. When it will acquire any charge by bombardment of electron, it is more likely possible that beta bond will get cleaved. See, this is alpha bond and this is beta bond. So this cleavage of this bond will occur. 1 electron will shift over here, 1 electron will shift over here, 1 electron from this pi bond will acquire here, and positive charge will be transferred to the ring. Okay, now this particular thing is product of McLafferty rearrangement. We are going to see it shortly. Okay, now what we are looking here is when CH2 will be formed, when cleavage of beta bond is there, we will get CH2. This 7 carbon structure will rearrangement into a 7-membered ring structure which is carrying a positive charge, which is electron deficient. The structure is called as tropylium ion with M by Z value of 91. Now, next rule. Next, cleavage is often associated with elimination of small, stable, neutral molecules such as carbon dioxide, olefins, water, ammonia, hydrogen sulfide, hydrogen cyanide, mercaptans, ketones, or alcohols are often with rearrangement. Now, this point number 8 we are going to see in detail in few of the further rules. See, factors influencing fragmentation process, bombardment energy. If it is high, you will get more and more fragmentation. Functional group, different functional groups react to fragmentation in different ways. Then thermal decomposition. Okay, let us see general modes of fragmentation. We had seen rules before. Now let us see general modes of fragmentation. Now, fragmentation of the molecular ion takes place in following modes. One is simple cleavage, and second is rearrangement reactions are accompanied by transfer of atoms. In simple cleavage, there are three types of cleavages that are possible: homolytic cleavage, heterolytic cleavage, and a retro-Diels-Alder reaction. In rearrangement type, first we have scrambling, then we have McLafferty rearrangement, and we have certain elimination reaction. Now, let's start with homolytic cleavage. Here, fragmentation is due to electron redistribution between bonds. So you have one alkane. Okay, suppose this double bond we need to express in a slightly different manner. So how can we express that? We can express it as there are two electrons between these two carbons. Okay, so it is the same structure. When we will bombard this molecule with electron, one of the electron is likely to get removed from the structure. Then the homolytic cleavage, if it has to occur, there are two possibilities. Okay, if you can imagine, the possibility may be the remaining electron will go to one of the CH2, so the other will acquire a positive charge. Okay, this is like we are dividing this bond into two equal halves. Okay, if homolytic cleavage is occurring in a neutral molecule, not in ion, it will look something like this. Just a second, I will display it. If it has to be homolytic cleavage, one electron will go on this carbon, the other electron will go on this carbon. So you will get two fragments after homolytic cleavage as R1C and R2C. If it has to be heterolytic cleavage, then there are two possibilities. Two possibilities are, one possibility that both the electrons are going to one carbon, giving you R1C minus and R2C plus. The other possibility is both the electrons are going on this carbon. Then you will get R1C plus and R2C minus. So this is example of homolytic cleavage, and this is example of heterolytic cleavage in neutral molecules. Now please remember, we are not here talking about ions, we are here talking about molecules in this example when we look at homolytic and heterolytic cleavage. But in mass spectrometry, we are more likely to encounter ions. So this positively charged and a neutral molecule signifies that this is homolytic cleavage. Now coming to the heterolytic cleavage. Now heterolytic cleavage within the ions. Okay, ions produced after ionization of the neutral molecule, neutral sample. Now fragmentation by movement of two electrons. Okay, in previous scenario it was movement of one electron. Now movement of two electrons will take place. Now in this type of cleavage, both electrons of the bond are taken over by one of the atoms. Easy to understand. The fragments are even. Fragments are an even electron cation and a radical with positive charge residing on the alkyl group. It is designated by a conventional arrow, that is full curved arrow, to signify the transfer of pair of electrons in the direction of the charged site. So the ether, when it was ionized, it produced oxygen that was carrying a positive charge. So both the electrons between oxygen and alkyl group shifted on oxygen, giving you R as positive and this OR radical. Okay, the simplistic expression is between XY molecule as it is shown over here. You can also see the example over here. I will give you some time to observe. You may ask your doubts if you don't understand anything. Okay, proceeding further. Retro-Diels-Alder reaction. You must be remembering Diels-Alder reaction. I will quickly show you what is Diels-Alder reaction, then I hope retro-Diels-Alder will be easy to you. So Diels-Alder reaction is between diene, which I have drawn on the left hand side, and dienophile. Okay, dienophile can be anything, like I have drawn one alkene over here, but dienophile can be anything. It may be acetylene also. Okay, it may be some carbonyl group also. Okay, anything that contains a double bond or triple bond may form dienophile. Anything that is attacking diene, okay, it is called as dienophile. So how the reaction proceeds is, see, dienophile, okay, this fellow over here will first attack the diene over here at the you can say uh, at a pi bond carbon. Okay, so there is shifting of this pi bond over here. Okay, and this pi bond will form a sigma bond between these two carbons. So what happens is we will get one intermediate stage where now I am drawing one intermediate. Okay. Okay, so this is the intermediate. If I want to draw it simplistically, I will draw it like this. Okay, there is definitely aromaticity associated with this. Okay, so when this what we can say intermediate complex, intermediate adduct, when it is completed, it forms structure something like this. So we started with diene and dienophile, and we got this structure. So two of the pi bonds converted into a sigma bond. Okay, these are the new sigma bonds formed due to shifting of pi bonds, and there is shifting of one pi bond, delocalization or shifting of one pi bond. Okay, if this is Diels-Alder reaction, retro-Diels-Alder means in the reverse manner. Okay, it is in the reverse manner. So in that, what will happen? Two of the sigma bonds will give you two pi bonds by shifting, and there is shifting of one pi bond. We will start with one structure and we will end up into two structures. Elimination of multiple sigma bond, elimination by multiple sigma bond rupture. We have seen that sigma bonds are shifted to form pi bonds. So cyclohexene is broken down to diene and dienophile. It can be explained by one or two electron mechanisms. So one of the mechanism is, try to zoom in. Okay, see, this is cyclohexene. Electron is lost. We can show that by formation of radical and positive charge. So first mechanism is showing shifting of electrons, single electrons, not pair of electrons, single electrons. So from one of the pi bond, one electron is shifting over here. The other electron it will receive from this sigma bond. So one electron from over will come over here. So there will be formation of pi bond over here in the process, because one electron shifted from this sigma bond over here, this sigma bond will cleave. So this single electron will shift over here. Okay, so remaining one electron from this pi bond will come over here. One of the electrons from this sigma bond will come over here. Okay, so there will be formation of new pi bond between these two carbons. The remaining electron will shift over here to form a pi bond over here. So you can see over here. So this is called as one electron mechanism, where we are shifting only one electrons at a time. In two electrons mechanism, you can see that the entire pi bond is shifting over here. This entire sigma bond is shifting over here. So there is cleavage of this sigma bond, formation of pi bond over here. The moment this pi bond is shifting over here, the entire sigma bond is shifting over here to form a new pi bond over here. In both mechanisms, you will get two products. I hope it is a good revision for you. Then next comes rearrangement reactions accompanied by transfer of atoms. First type is scrambling. Now please focus that there is transfer of atoms. Atoms are being transferred. Okay. So first type, as we had seen in the listing also, first is scrambling. Fragmentation giving rise to stable carbocations. So the product will be a carbocation which is stable. In certain cases, fragmentation takes place at bond, which gives stable carbocation. For example, let us see the example. Okay, removal of alkyl group. Okay, alkyl group removed as this electron is shifting over here. Formation of the pi bond will also shift, giving rise to this structure. It will rearrange itself into propylene ion. Next is McLafferty rearrangement. Now, McLafferty rearrangement, there is shifting of hydrogen. We have fragmentation due to rearrangement of molecular or parent ion. Here, cleavage of bonds in molecular ion is due to the intramolecular atomic rearrangement. It is within the molecule. This leads to fragmentation, whose origin cannot be described by simple cleavage of bonds. There is shifting of atoms also, shifting of group also. When fragments are accompanied by bond formation as well as bond breaking, a rearrangement process is said to have occurred. Such rearrangement involves the transfer of hydrogen from one part of the molecule to another via preferably six-membered cyclic transition. This process is favored energetically because as many bonds are formed or as broken. So there is no net change in the energy. Okay. Compounds containing hydrogen atom at positive gamma 2 carbonyl group have been found to a relative intense peak. This is probably due to rearrangement, and fragmentation is accompanied by loss of neutral molecule. This rearrangement is known as McLafferty Rearrangement. So this is the pi bond we are talking about. Okay, this is alpha, beta, and gamma carbon. On gamma carbon there is hydrogen. So at gamma carbon there has to be one hydrogen. Now when we from where we have to start counting alpha beta, from a bond adjacent to a double bond. Okay, so the rearrangement takes place like that. We have a positively charged heteroatom. So this hydrogen along with its electron is shifted on to give you hydroxyl group. The moment this shift takes place, this pi bond is shifted between the next two carbons, which will further push cleavage of this bond to shift between these two carbons, and a neutral olefin is removed, and we got phenol, which is positively charged radical. Now there are certain criteria for rearrangement. To undergo McLafferty rearrangement, molecule must possess an appropriate location of heteroatom. For example, oxygen. Okay, so heteroatom must be present, a double bond should be present, an abstractable hydrogen atom which is at gamma to CO system. So in this table you can see McLafferty peak in the spectra of different carbonyls. Okay, so if it is aldehyde, you will get at 54, methyl ketone 8, amides 9, acid 60, 72, methyl ester 74, and so on. Okay, next is elimination type. The fragmentation due to loss of small molecule, loss of small stable molecules such as water, carbon dioxide, carbon monoxide, C2H4 from molecular ion during fragmentation. Example, you can see that in alcohol where water molecule is removed. An alcohol readily loses water molecule and shows peak at 18 mass unit, less than that of the peak of nuclear ion. So this is butanol, N-butanol to be specific. When it will acquire a charge, it will acquire charge at oxygen. So when fragmentation takes place, actually this removal of water molecule from here takes place, where the hydrogen from here gets shifted on oxygen. So you get CH positive over here. You can see that. Okay, so water molecule is removed. Fragmentation adjacent to branching point. This we have seen before in alkenes, so I will skip this point. Then come to the fragmentation patterns and fragmentation characteristic related to certain types of functional group. Let us first start with saturated hydrocarbons. In saturated hydrocarbons, there are possibilities like there will be a straight chain compound and there will be a branched compound. So if it is straight chain, let us see what are the rules. The relative height of parent peak decreases as the molecular mass increases in the homologous series. We have seen this rule before. The molecular ion peak, although it may be weak, it is normally present. But as the number of carbon increases, the height of this molecular ion peak goes on decreasing more and more. The spectra generally consist of cluster of peaks separated by 14 mass units corresponding to CH2 groups. The largest peak in each cluster represent CnH2n plus 1 fragment. Now, where this fragment must be coming from? Any idea? This is accompanied by CnH2n and Cn2n minus 1 fragment corresponding to loss of 1 or 2 hydrogen atoms respectively. Let us see what happens to branch chain hydrocarbons. We have seen this. At the branching, the fragmentation is likely to take place. Uh, most stable chain, which is least ionizable, will carry the charge, and the longest chain, which is capable of carrying radical, will be separated. So what happens in alkenes? In alkenes, generally formation of allyls. Okay, generally formation of allyl that will have M by Z of 42. This formation will be preferred, one thing, and if there is a gamma hydrogen, McLafferty rearrangement is likely to take place. Okay. If these cycloalkanes, retro Diels Alder will take place. Now, in case of aromatic compounds, see, in aromatic compounds, this aromatic ring along with this carbon, okay, this will remain stable, and cleavage will take place at this beta bond. So R will get cleaved, and this 7-membered will ultimately form propylium ion. We have seen one example of alcohol. So in alcohols, the fragmentation will take place depending on whether it is primary, secondary, or tertiary carbon. These peaks of mass spectrometry can actually distinguish between 3 types of alcohols: primary, secondary, and tertiary. Okay. The molecular peak of primary secondary alcohol is usually of low abundance. It is not detected at all in tertiary alcohols. The fragmentation modes in alcohols depends upon the fact whether it is primary, secondary, or tertiary. The fragmentation of carbon-carbon bond adjacent to oxygen atom is preferred fragmentation mode, that is alpha cleavage. So alpha cleavage that we have studied before will be favored for alcohols. Primary alcohol shows M minus 18 peaks corresponding to loss of water molecule. The long chain members may also show corresponding peaks corresponding to successive loss of oxygen radicals at M-1, M-2, and M-3. The CH2OH is most significant peak in the spectra of primary alcohol. So this peak will always be there in primary alcohols. In case of secondary alcohols, cleavage to give prominent peaks due to RCH11OH at M by Z 45, 59, 73 will be observed. Now, in case of aromatic alcohols, the pattern of fragmentation will be relatively similar. So, the relative abundance of the parent ion aromatic alcohol is large. Some of the fragment modes of benzyl alcohol are loss of 1 or 2 or even 3 hydrogen atoms. Now, in case of alcohols also, if there is McLafferty rearrangement, it may take place. Okay, M plus H fragment of benzyl alcohol also rearranges to form hydroxyl tropylium ion. So the tropylium ion mechanism that we have seen over here, there may be hydroxyl group involved and the fragmentation will remain similar. In case of aldehyde and in case of ketones, see, alpha and beta cleavage is possible. So for aldehydes, loss of hydrogen, alpha hydrogen will take place, and second common feature of aliphatic aldehyde is beta cleavage. Now, in case of ketones, along with alpha cleavage, there will be McLafferty rearrangement also.